We're at the top of page 8. It's periodic table time. Comes with matching underwear. I don't think you want to see the rest. Anyway, the elements in the periodic table are arranged in order of increasing atomic number. The atomic number, if you recall, is the number of protons. The atomic number is what identifies an element. So the elements are not arranged alphabetically. H, which is element number 1, is not the first letter in the alphabet. They're not arranged according to increasing atomic mass. That would be a wrong answer, even though it seems that way. Let me show you that there are some discrepancies. For example, if you compare the mass of argon, argon is 39.948, with the mass of potassium, letter K, it's 39.0983. So argon is heavier than potassium, yet in order, argon is number 18 and potassium is number 19. So it's not by mass. I'll show you another discrepancy. If you look in the crease of your table here between cobalt, CO, and Ni, it reads cobalt, which comes before nickel, is 58.9, and yet nickel, which is next, is 58.69. So there are the discrepancies. The elements are arranged by atomic number, not mass. The table in which the elements were arranged by mass was the first table, Mendeleev's table. All right. Now, in general, and this is in general, elements in the same group have the same number of valence electrons. We refer to the groups as families. The reason for that is the groups being the columns, which are up and down. And take a look at your table. There are 18 groups or columns, up and down, from 1 to 18. And I like to refer to them as families because elements in the same group or family, since they have the same number of valence electrons, they have similar properties. So, same group, same number of valence electrons. And that would give us similar properties. In fact, that's the greatest similarity. Elements in the same period, on the other hand, have the same number of orbits or energy levels, shells, or whatever you want to refer to them as. So same period, same number of orbits. So again, let's illustrate. Let's go to period 3. Remember, the periods go across. They're the rows from left to right. And the groups go up and down. So in period 3 and period 4, you'll find Na and K. Potassium, K, sodium on top. They're both in group 1. Notice since they're both in group 1, they have 1 valence electron. On the other hand, to the right, magnesium and calcium are both in group 2. They'll have 2 valence electrons. 2 VEs. So, sodium and potassium are in the same family. What that family is, we'll see in a second. And magnesium and calcium are in the same family, meaning sodium and potassium will behave more alike than magnesium or calcium, and magnesium and calcium vice versa. All right. Then, as far as the periods are concerned, both sodium and magnesium, the only thing they have in common is that they are in period 3, so therefore they have 3 orbits. 1, 2, 3. 1, 2, 3. So, 3 orbits, shells, or energy levels. 4th period, 4 orbits. Potassium is 1, 2, 3, 4. 1, 2, 3, 4 for calcium. Now there's something really, it's just the way it's worded, it sounds confusing. And that is, elements in the same period have also this in common. That is, they have valence electrons in the same orbit. Let's read it again. They don't have the same number of valence electrons, they have valence electrons in the same orbit. So, sodium and magnesium, for example, have 3 orbits each. In the 3rd orbit is where you find the valence electron of sodium. It has 1 valence electron. In the 3rd orbit is where you find the valence electrons of magnesium. It has 2. So it's a little confusing, so that's why I put a star by it. periodic table is a real easy unit. You can get a piece of paper towel so we can wipe this. It's a real easy unit. I want to get points on that soon. Now, let's look at some properties, some physical properties of metals compared to, contrasted with non-metals. Remember, most of the elements are metals. Metals are to the left of the step border. And that's something you should mark out right away or notice in your periodic table. Once again, there is a step border. I like to call it the bat line. A friend of mine came up with this, the bat line, like Batman. Da-na-na-na-na-na-na. Batman, bat line. And then to the left, you have the metals. And you'll see most of the elements, over 2/3 of them, are metals. Metals are to the left, they're losers, chemically. And physically, since 1 2/3 are metals, most of your elements are all solid. Metals are solid, except mercury. Mercury is a liquid. Your metals are malleable and ductile. Malleable means they're hammerable. It's hammer time. You can hammer them into thin sheets. Ductile means that they are wireable. In other words, you can pull them into wires. And of course, metals have that color, that silver gray color, except of course for copper and gold. Cu, copper, and Au, they're both gold colored. And then metals, of course, are shiny or have luster, which is a fancy way of saying that. And they're good conductors of heat and electricity. All right. Non-metals, you can think of them as opposed to metals, are the opposite. Non-metals can exist, and you have non-metals in all three states. There are non-metals that are gases, or liquids. Well, there's one that's a liquid, I should say, and the rest are solids. They're brittle, which means is they're the opposite of malleable and ductile. They crack easily if they're brittle. So if you hammer a non-metal, like a piece of glass, it breaks into pieces. Non-metals are not limited to a silver gray color. They come in many colors. Non-metals are not shiny, they're dull. They are poor conductors, not good conductors. So brittle and dull is a good thing to remember. All right, and then below this, I have just a mini periodic table which gives you the important points to remember about the different families. So what I'm going to do is just reduce this a little bit so I can get the next slide in. So what I have here is just a mini periodic table with some facts you ought to know. And really this part of the periodic table, this part of the unit, is just facts. Some facts you ought to know about the different families. All right, and the first family here, first of all, you should know that they're called the alkali metals. And we list them to fill in this table here. So we have Li, then Na for sodium, K for potassium, Rb, rubidium. Remember the symbols are listed with their names in table S. And Fr, that one you ought to know. And give it a crown, we'll give it a Burger King crown. That's the king of metals. That is the most active of all the metals. So the alkalis are the most active metals. And because of that, they're found naturally only in compounds because they're so willing to react with non-metals that if you wanted to get sodium, you'd have to extract it from a compound, all right, as an example, or any of these. All right, and the way we extract them, we free them from their compounds, is through a process known as electrolysis, which I mentioned before in the first unit. So that's good to know. And then I'll elaborate on that with an example as soon as I raise this page. And then in group 2, we have the alkaline earth metals, and that's really what you need to know about them, their name, and that they're the second most active or most reactive metals. And let's list them as an exercise to fill this table. In general, if you interact with your notes, you're more likely to remember it. And I mean fill in, color, do whatever it takes, otherwise this becomes way too passive. And you end up falling asleep from the boredom. So, and then RA. And then in the middle of the periodic table, that is groups 3 to 12, we have what are called the transition elements. So you don't have to know the individual names of those families, but two things is what the transition elements have in common. One, they have multiple, more than one, oxidation states. For example, if you look at element number 22, Ti, 2 plus 2 plus 3 plus 4. Look at V, vanadium, element number 23, plus 2 plus 3 plus 4 plus 5. So in general, they have multiple oxidation states. There are some that just have one. And the example I have here is that of copper. Copper has a +1 and a +2 oxidation state. So when copper +1 reacts with chlorine, you form copper Roman numeral 1 chloride. And that Roman numeral 1 doesn't indicate the order in which it appears, but instead it indicates the actual charge or oxidation state of the copper. Then when copper reacts with chlorine with a +2 oxidation state, the copper +2 with chlorine forms copper Roman numeral 2 chloride. So those are called binary compounds, more than one binary compound, because they consist of only two elements. And we'll get more into this again in formula writing. And it's off topic to really do formulas here now. And secondly, they form colored ions. They impart color to their compounds. So if it has a transition element, the color is due to the transition element. And then, as we're moving across the table, why don't we first come across here and hit mercury, put a star by it, 2 stars, because mercury is a liquid. And there are only 2 liquids in the entire periodic table, mercury and bromine, which you'll find down here. I'll star that in a second. And while we're here, let's darken the bat line, or the step order, to remind you that the elements that touch either side of this, B, except Al, of course. Al is not. Al is not a metalloid or semi-metal. It's a metal. SiGe, As, Sb, Te, PO8. We'll call those the metalloids or semi-metals. There's some debate as to the ones towards the bottom, but you're fine with that to remember it that way. Okay? And then moving to the right again, I want you to note something called the radioactivity border, which is past element number 83, starting with element 84, all of the isotopes of this element, polonium, PO, are radioactive, and all the isotopes of the next element, At, will be radioactive, etc. Now, for 83 and below, some of the isotopes are radioactive. Which ones, you'd have to be told. So when we say radioactive, we mean it gives off alpha, beta, or can it give off gamma, or a combination of these? And we'll learn more about that in radioactivity. All right, so again, these are all facts that are tested in this unit. Then we should note, in group 17, you don't have to know the elements in group 13 by name, their family name, or 14 or 15 or 16, but you ought to know that group 17 contains the most active nonmetals, which are the halogens, beginning with fluorine, and then comes chlorine, then comes bromine, and iodine. We'll exclude At, astatine, because astatine is more of a metalloid. And let's put a crown at the same time on fluorine, because fluorine is the king of nonmetals. It is the most active of the nonmetals. just as francium is the most active of the metals. And then in the last group, last but not least, we have the noble gases. Let's list them, beginning with Ne, neon, Ar, argon, Kr, krypton, Xe, and Rn, neon and radon. Okay, and these are the noble gases, and what they're known for is the fact that the noble gases are chemically inactive. I'm trying to find my cursor here. Okay, just to keep the screen on. So the noble gases are inert, chemically inactive. And the reason for that, as I said before, is that they have what is called a stable octet. So those 8 electrons make them chemically inert. All right. There are exceptions, which we'll mention in a second. And also, I mentioned here that helium, also noble gas, doesn't have an octet, it has a doublet. So that's why you'll see that helium is detached from the table in the periodic table to remind you of that. So it's a noble gas, but it's detached because it has a doublet, not an octet. All right. Let me erase this. Elaborate some more at the bottom, and then I'll repeat what I just said about helium and before that hydrogen. The two that are detached from the table. Okay, let's slow this down a little bit. Some room there. And let me give you that example of electrolysis here. So if you take some sodium chloride, fused, in other words, as a liquid, you add electricity to it, it's electric. Alright, you'll end up making, as a result, sodium as a solid. You're going to need 2 parts sodium chloride, and chlorine as a gas. Notice that 2 again. We'll talk about the 7 elements, the Hankel-Briefs, as some people put it, that are diatomic. Then the alkaline earth, we've covered that. The halogens, let's put a double star by the bromine, because it's a liquid. There are only 2 liquids, as I said for the mercury. I'll remind you again. And then notice, too, that the halogens are the only family in which you'll find all 3 states, meaning solid, liquid, and gas. And again, this point here about the noble gases being monoatomic, what that means is whenever we write a noble gas, like helium, we write He, not He2. That would make it diatomic. And then krypton and xenon, if you look at your periodic table, krypton and xenon have positive oxidation states, in addition to the most common 0, which means they do nothing. So krypton and xenon, krypton has a 0 and a +2 oxidation state. And xenon has more than that, has 0, +2, +4, +6. And that indicates that they can be forced to react, though in the normal circumstances, with most elements, they do nothing. All right? Oh, there's a little color here too, huh? Just want to make sure we don't lose this image, since I have more information to tell you than this screen probably allows me. Just get that for a second. And let's lift that up too. But final thought on the noble gases before we go to the top here is you can play with this word here, noble. Might help you to remember the O here for the octet of VE, valence electrons. All right, which that's why they have the 0 oxidation state, which indicates they do nothing. They are inert. They do nothing. Okay. And finally, on this page, I want to move it up. I'll bring you to the top here. And I want to mention, once again, why we detach hydrogen only in your table for the Regents. All right, and hydrogen is detached to remind you that hydrogen is not an alkali metal. Think about it. Can't be. All right, so hydrogen says, I'm not a metal. With attitude, I'm not a metal. It's grouped here. It's in this column because it has one valence electron. Going to the extreme, the other element that's detached is the helium, Ag, and helium says, I don't have an octet. Exclamation point with attitude. All right? Or, another way of saying it is, you could say, me too, as one of my students once suggested. And that's really a play on words, because he's saying, I'm also noble gas, but me too, I have a doublet, not an octet. All right, so now that's a lot of information that I just gave you. They are unrelated facts that just keep looking at these notes, study them by doing problems, and you'll master these points. And if you find anything else that's tested and I haven't listed here, then interact with the notes and add to it. But this pretty much covers it. All right, now we're going to turn to the next page and we're going to see the so-called thinking questions on a periodic table. And that is questions related to some key properties that change as we go up groups into the right of periods. So I'll meet you there.